Welcome to lecture 12. Here we're going to continue our discussion of line fitting, particularly looking at a general form of linear least squares and nonlinear regression. First, of course, I'd like to start off with reviewing what we covered in the previous class. Remember, we talked about basic statistics, including locations of data and spread of data, and then several variations of that, particularly averages, standard deviations, and variance. We use those concepts in combination with calculus to find slopes and intercepts of the best fitted lines using a sum of squared error. We then used coefficients of determination to estimate the error of our line fit. We then talked about how we could transform some equations from nonlinear equations into linear equations such that we could do linear fit on them. And then finally, we talked about linear regression in MATLAB. Today, I'm going to continue that discussion talking about polynomial regression rather than just linear regression. Then we'll get into multiple linear regression, excuse me, general least squares models, and then how we can implement nonlinear regression with optimization techniques. In general, the strategy for this entire class is going to be to turn our equation into some form of linear form. Then we'll formulate some sort of sum of squares error. We'll form a series of linear equations from those sum of squares equations, and then we'll solve for coefficients using linear algebra. So let's start out with a discussion on non-linear equations. So if we just took, say, this data set over here, we can see that we could fit a line to it. However, that line wouldn't be very representative of the data. This a parabolic fit would more accurately represent that data. So what we're going to do, as I mentioned before, is recast that the problem of fitting a non-linear equation, or fitting a parabolic equation into fitting a system of linear equations. So we're going to do this using sum of squareds. So let's first look at the equation that we're looking for. If we want just a generic parabolic equation, we could say that y equals some constant a0 plus a constant a1 times x plus a constant a2 times x squared. Once again, we're going to use this idea of a sum of squares, or a sum of our residuals, in order to see how wrong or right an equation is. So if you remember from last time, we can say our sum of residuals is the sum over every point yi minus the equation, the y calculated using our fit equation. In this case, it's a0 minus a0 minus a1 xi minus a2 xi squared. And then we square that difference just so we don't end up canceling out error due to having opposite signed sets. So the idea is we're going to minimize this least squares by taking a derivative with respect to each constant and setting that derivative to 0. Let's do that now. So we want to take the derivative of SR with respect to A0, our first unknown, and we're going to set that to 0. So if I look through here, remember that my definition of that chain rule is going to be the derivative of the outside, so this 2, times the derivative of the inside. So minus a0 minus a1 xi minus a2 xi squared times the derivative of the inside. The derivative of the inside of SR with respect to A naught is 1. So we end up with this equation that says 2 times the sum over all of our i's of x yi minus A naught minus A1 xi minus A2 xi squared times 1 equals 0. And we can continue this for each of my individual constants. So the outside's always going to be the same, right? Because I take that derivative of the outside. So I always end up with this yi minus A naught minus A1 xi minus A2 xi squared. And now I look, what's my derivative of this equation with respect to, or of the inside with respect to xi? Well, it's xi. Sorry, now with respect to xi with respect to A, it's xi. So we get this nice 0. And then we can do this again, SR delta A2 is 0 twice the sum of xi minus A naught minus A1 xi minus A2 xi squared. The derivative with respect to A2 is just xi squared. We're going to set that all equal to 0. So we now have these three equations describing the condition where x1 is a minimum, x2 is a minimum, and A1 is a minimum, A2 is a minimum, and A3 is a minimum. So now we're ready to put this into some form where we can get each of these A's alone. So we need to get each of these A's alone so that we can conduct our, or actually come up with an end value. So we should tackle that first equation. So we're going to rearrange this equation. Remember, it's -2 times the sum of y1 minus A0 minus A1 xi minus A2 xi squared. And all of this is going to be set equal to 0. So the goal in this case is going to be to get A1 or A0 alone. We want to get A0 all alone because we're going to tackle this equation first. Right. So we can first divide by 2 because that's just a constant, and then we're left with this equation within the sum. Because I don't have any multiplication, I can take each of my summations separately. So I get a sum of yi, a sum of A naught, minus a sum of A1 xi, minus a sum of A2 xi squared, and that all equals 0. Right? So now we can take our next step. We can look at each of these cases and try to pull any constants out. So I can't pull any constants out of that yi, so I'm just going to leave that alone. So you have a sum of yi. Here, remember this is going from I equals 1 to n. So if I take n plus n plus n plus n, A1, A0 plus A0 plus A0 plus A0 n times, I have n times A0. Similarly, I have this constant A1, which I can pull out of the equation, right? Because that's going to be a constant. So I can have A1, and then I have this summation of xi, and then I have the same thing over here. I can pull that A2 out of the equation, and I have the sum of xi squared, and still equal to 0. So now I can rearrange this so I have all the a's on one side and anything that doesn't have an a on the other side. Right? So if I do this, I have n times a naught plus a1 times my sum of xi plus a2 times the sum of xi squared, and all that is going to be equal to the sum of my yi's. So this is going to be the first equation that we're going to use to solve for the different constants a0, a1, and a2. I'm going to, and I've put that over here. Maybe I'll erase that just to clarify. Great. So this is going to be our first equation that's we're going to use to solve for these coefficients. So we're going to redo this again with the second round. So I'm just going to pull down this equation. Once again, I can start out by dividing by that 2. So we're left with the sum of xi times yi minus a0 minus a1 xi minus a2 xi squared, and all of this is going to be equal to 0. So I'm going to do the exact same thing that I did before. I'm going to distribute the xi's through here and then separate each individual term into its own summation. So we have the sum of xi yi minus the sum of a naught xi minus the sum of a1 xi squared minus the sum of a2 xi cubed. Right. All I've done is I've distributed this xi through and separated each summation. Okay. Now I can once again separate everything that has an a to one side, everything that doesn't have an a to the other side. When I do this, I have my sum of xi yi equals that sum of a0 xi minus the sum of a1 xi squared minus the sum of a2 xi cubed. So this is going to be our second equation that we're going to use for solving these lines. Here we have the sum. All I've done in this case is I've pulled those individual a's outside, right? These are constants, these different a's are constants, so I can pull them out of the summation. And here on the right, I'm reflecting that these a's have been pulled out by making sure that those summations are in parentheses. Now we can do this with the third equation. Once again, we're going to drag that third equation down. I'm going to do this one a little bit faster. We have the sum of xi squared times yi minus a0 minus a1 xi minus a2 xi squared. All this equals 0. I'm going to distribute this through. I have xi squared yi minus some xi squared a0 minus some xi squared a1 xi minus some xi squared a2 xi squared. All this equals 0. So now I'm going to pull these down and pull out each individual xi. So that gives me the sum of xi squared yi is equal to a0 sum xi squared minus a1 sum xi cubed, plus a1 sum of xi cubed plus a2 sum of xi to the fourth. Right? So once again, we've isolated all these things, and we have this third equation written out right here that we're going to use. What you'll notice is I've written these equations in a very particular way, especially when I bring them all together. Here, we have all of these constants on one side, a series of numbers that we know, right? We can relatively easily calculate, and we can relatively easily calculate the sums of xi's, xi squared, xi cubed, etc. And then we have three sums of y times some value. Well, hopefully this looks very familiar, because this is, in essence, a linear algebra problem. I can pull out each of these A0, A0, A1, A2, and put this in a linear algebraic form. Now that I have it in a linear algebraic form, well, I know how to solve that, right? We've spent 2 or 3 weeks talking about how to solve these problems. Now, all we need to do to solve this is fill in each of these entries into the, say, A vector and that, A matrix and that B vector through computation, and we're ready to go. Great. So this provides us a way to assess the, or rather to extract the coefficients of my equation y equals a0 plus a1x plus a2x squared, right out of this formula. But in addition to knowing a0, a1, a2, we probably want to know a little bit about the error, and we want to be able to measure how good my fit is. So we're going to go back to this concept of my sum of residuals and my variance of the y values. So remember, my SR, my sum of my residuals, is the sum from I to n of each data point that was given minus the y that's calculated. I'll put this in green. So this is the calculated y's from our different equation. These are the data points that we're trying to regress to. And then just to go back and remind ourselves, my variance in the data is still my sum from over each data point, where I then look at how much y differs, each data point y differs from the average value of y squared. So just that variance within my y's. We can now compute standard error. Here we're going to represent it, the standard error of y as described by my x's. That is SR over n minus m plus 1. Here, n is once again the number of data points, and m is the power of the exponent of x. So remember, we were fitting a0 plus a1 xi plus a2 xi squared. This 2 would be m. If I was fitting a cubic form, that m would be a 3 to the 4th power 4, etc., etc. So in this standard error, I have both my residuals, my sum of my residuals. I have how much data I used to calculate my fit, and then I have information about how many powers I fit this to. Once again, we can have a coefficient of determination. Oops. Once again, we can have a coefficient of determination, so our r² value. This is going to be the same as before. We look at the variance in y via st minus the sum of squared and the residuals. So how much variance still occurs once I fit my function all over how much variance was in my system originally. Okay, let's put this into an example. Here we're going to fit a quadratic function using least squared fits to a data set shown over here. After we have that data set and the fit, we want to determine the coefficient of determination. So let's first write out the equation that we're trying to solve. So we have y equals a0 plus a1x plus a2x squared. Since we're pulling out a quadratic equation, I'm just going to pull those matrices forward that we solved for earlier. Right? So this is going to be our set of matrices that we need. In this case, we need to know a whole bunch of information about sums about our different pieces of data. So rather than sit here and actually write out all of the summations, I've compiled that data here already. So let's look at these individual pieces really quick. So here we have m equals 2 because we're looking for a quadratic. We have m equals 6 because I have 6 data points. 1, 2, 3, 4, 5, 6. Our average x we can calculate in the normal way, where I'm going to sum up all my x's and divide by 6, and then same thing with my individual y's. Then once again, we can go through, we can sum up each individual x, we can sum up all the y's, we can first square each x and then sum those numbers, we can cube each x and sum those numbers, take x to the 4th power, sum those values, take x times y, sum those values, and then take those x squared values, multiply them by yi, and then sum them together. So here I've gone through and done all that math for us. So now we just need to take this information and put it into this format. So I've gone ahead and done that on the next slide. So here we have all that data that was entered in sort of tabular form into our matrix. Now we have this nice matrix. You wouldn't even know that we're trying to do line fitting, right? But in the way that we formulated this this data, it's going to force us to have when we solve this out, we will get our best fit. So now we're going to go in and use MATLAB to solve this out. So here we are in MATLAB. I've gone in and typed in our different values for n and the different values for r from that previous slide. So just to show you, we have our n matrix. We've got r that's representing those vertical cases. I'm now ready to conduct my linear algebra. We can then say that my a values are n back divided by r, right? So when I hit enter, we have these values that are popping up. And so these different values are showing a0, A1, and A2. So I now have my equation for each of these cases. So we have, right, y equals 2.4786 plus 2.3593x plus 1.8607x squared, right? So you can see now that we're, with a little bit of math and a lot of taking different sums, we're able to carry out and figure out the equations for nonlinear, the constants of nonlinear equations like polynomials by recasting these as a series of linear equations in A and then doing some linear algebra. Okay, let's go back to PowerPoint. We can talk about our investigation of the error. So now we're ready to look at our different values of the error. So remember our standard error, so sy over x, is equal to the square root of SR over n minus m plus 1. So this means we first need to calculate SR. So SR, as you remember, is the summation of each data point minus the function value from our fit squared. In this case, y equals a0 plus a1x plus a2x squared. From MATLAB, we're able to say what these different a's are. So we can say that SR is equal to each individual point yi minus 2.4786 minus 2.3593x minus 1.8607x squared. Once again, I'm not going to go in and do all of these calculations in front of you. You'll get quite bored, but in the end, this ends up being 3.74657. You can go ahead and punch these numbers into your calculator and just double check my math. So now that we have the standard, now that we have the sum of our residuals, we're ready to go back and look at our standard error. Remember, we can plug in that SR value. And then we just need to know n and m. Remember, we had 6 pieces of data, so n was 6. And then we are fitting to the quadratic, so m is 2. I'm going to put in my parentheses. So we have this overall equation. Right? So when I punch out the numbers, I have a standard error of 1.1175. So in general, my fit's pretty good. We can put this in terms of our coefficient of determination. So that our squared value, which is st minus sr all over st. And remembering that st is that variance in y. Not doing this out, but this ends up being 2513.39. So I can just plug these values in there because I already have SR from up here. So I have ST, so 2513.39 minus 3.74657 over 2513.39. Punch all this out, you end up with 0.99851. Right? So my coefficient of determination is very close to 1. Right? I have very little error in this SR. I'm looking in comparison to how much variation I have in my Y data. I'm looking very good, and I have a good fit. Hopefully, this has taken you through these equations for a quadratic fit. And then we'll just make a quick comment about how we can apply these ideas to larger systems of polynomials. So let's go back very briefly to those equations that we derived by taking our partial derivatives. Now, you could come in and for each additional vector that you saw, you could then, for each additional degree or order of the polynomial, you could resolve out all of those equations. Or you could start to recognize that there's a pattern here, especially as I go, if I go and I look at that matrix. As I move across each row, we see that the order in X increases by 1, right? So I go from 0th order, first order in X, second order in X, right? Then if I go down to the second row, I'm also increasing by 1 order. I go from 0th order in X to first order in X. But then I still am increasing by 1 order as I move across, right? So if I sort of generalize this out, you could, to say a third dimension, you could say you would get this still n xi squared, and then the sum of xi cubed, right? So I can do this going down, sum of xi, sum of xi squared, sum of xi cubed, sum of xi to the 4th. And then this would go continue in this downward pattern of incrementing by 1. Same thing here. If I look at the a's, well, this is easy. I just add one more variable, right? It would be a0, a1, a2, a3. And then I've run out of space, so I'll go the other way. You can see this idea of adding 1 order to X applies here as well. So we could say sum of yi, sum of yi xi, sum of yi xi squared, sum of yi xi cubed, right? So we can turn this formula very generic. So this is going to stop our sort of discussion of single linear regression, and we're going to talk about how we can expand these regression-based ideas to multiple dimensions. Let's say that we're no longer considering just one or dimension where I have x and y. Let's say I'm now moving into 3 dimensions where I have x1, x2, and then this y as my 3rd dimension. So I'm going to have 2 independent variables and 1 dependent variable. So I can write this out as y equals a0 plus a1x1 plus a2x2. We're going to once again want to use linear regression to determine our a's. And it's going to follow a similar pattern to what we saw previously. The idea being that we're going to take this equation, calculate the sum of squares of our residuals, and then take the derivatives with respect to our different a's. So let's go ahead and do that. Our sum of squares equation is the sum of the residuals, is the sum from 1 to n of xi minus a naught minus a1 x1I minus a2 x2I. And then we squared that whole thing. Now we're ready to take my set of derivatives with respect to our different a's. These are going to look very similar to the equations that we wrote out for higher order polynomials. So if I take that first derivative with respect to a naught, I once again have that product rule going on where I have twice the sum of yi minus a naught minus a1 x1I minus a2 x2I, all in there, and then the derivative of what's happening on the inside, so the derivative of this equation, that inside equation with respect to a naught is 1. And so we're going to then set that equal to 0. Okay, so we're going to do this again for a2, so a little bit faster, sorry, a1. Once again, have that 2 come out. We have the inside of that product rule. Now we multiply that by the derivative of this inside with respect to a1. Well, that derivative with respect to a1, so I should have this with respect to a1, is negative x1I. And this all gets to be 0. And then we do this with respect to a2. It's going to be very similar. We have our sum yi minus a naught minus a1 x1I minus a2 x2I times what the derivative of what's inside this parentheses with respect to a2. Well, that's negative x2I. And all of this gets set equal to 0. Okay, so just like before, we have a series of equations where we have setters equal to 0. And we're going to now isolate each individual A and form a matrix. Okay, so not to belabor this point, but we have all these equations written out. I can do the exact same process where I take each of these individual summations, line them all up, pull out the A's, and then rearrange them to get everything with an A term on the left-hand side of the equation, everything with the Y term on the right-hand side of the equation. Since we already did that and it's quite a tedious process, I'm just going to write out the result. So we end up getting this equation with n, so the number of data points in the left in that 1, 1 spot, a sum over x1I in the middle spot, the sum over x2I in that second spot. Then once again, we're going to have this sort of, down repeating pattern, sum over the x1s, sum over the x2s, then sum over their products, x1, x2I. Okay, and then now we're going to do essentially the next bit, which is x2I, sum of x1I, x2I, sum of x2 squared. Right, and so then that's terrible vector sign. There we go. We have our A0, A1, A2. Right? And so then we can have all those terms now that are going to be associated with my y's. So if I sort of just look, you can see where those are going to come in. You can see where those are going to come in next. we have the sum of yi, the sum of x1i, yi, and then finally the sum of x2i, yi. Okay, so it's going to be the exact same idea, just with slightly different variables in here, but the same idea of look at the sum of squares equation, take a derivative, set that derivative equal to 0, and then for each a, and then isolate each of those a's to form this matrix formulation. Once this matrix is formed, we can go in using back division to solve for my different fits. We can generalize this out even further, thinking about linear equations, polynomials, multiple linear equations, really anything that's linear in the coefficients that we want to look at. Right? So these coefficients each have to be by themselves and linear. If we do this, we can call each of these functions labeled z as a basis function, right? So this could be a 1 or an x or an x squared, or even say sine of x or cosine of x or log x, anything that we want, as long as the coefficients are out front, right? So this is going to be the idea behind our general linear fit. So let's do a quick comparison, and then we can see how we can do this in this general way. So once again, here's our general linear fit. We have our coefficients, our a's, we have our basis functions, and then we have the error. So if we look at a few examples, we have that y equals a0 plus a1, x1 plus a2, x2. In this case, my first z, if I want to take this equation and turn it into that general form, my first z is a 1. My second set of z's are my x1s, and that second basis function is my x2s. Right? So I'm just converting this top equation, or this bottom equation, into that top equation by looking at how the z's are going to correspond in here. We can do that, say, again with this lower equation. In this case, we have z0 is still 1, z1 is now x1, and z2 is now x1 squared. Let's do another one just for fun. We have y equals a0 plus a1 x1 plus a2 natural log of x. In this case, z0 would be, once again, 1. My z1s would be those x1s. And that z2 would be, excuse me, the natural log of x2. So I can convert any of these equations, any equation, into this general form as long as all the equations are outside. So let's do maybe a counterexample. If I had y equals a0 plus a1 natural log x times a2, this I can't do, or maybe even better yet, x times natural log of x to the a cubed. We're now getting into trouble here. So let's now take this base case scenario and see how we're going to implement this. Into a linear algebraic formula. So we can take this equation, this generic equation, and rewrite it in terms of a matrix. So in this case, we have our vector of each individual y point, those z equations, right? So those different basis functions, times all of my coefficients that I'm looking for, plus the error, right? So that error is out here. That's everything that's not taken into account at each point. I then, let's look a little bit at each z. Here, going across each row, across each column are going to be my different z's. So, that's that 0, x1, x2, x1 squared, whatever. And then going down the rows are each different data point, right? So I have all of the row 1 represents all the x's, or all the different z's for one point that's going to go into y. And then the next row is, say, 0.2, and the next row is 0.3, etc. So in the z, we can represent them by indices. That second index is going to be represented as the data point. So if I have n data points, we have this n here. And then this m, so that first number over on the right hand, is the number of functions, the number of basis functions we have, right? So how big is this equation up top? Once we've built this function, we still need to minimize the error. This is because z is usually not squared. If it was perfectly squared, we had exactly as many data points as we wanted, we could solve this out. Remembering we have, we could move those across. But since it's usually not square, we need to minimize the sum of my squared errors. So we need to minimize this equation. So dsr dai. Or I guess here it's aj. When I go and do that, the sum of my minimization looks like this. I have this z transform z term out front. This is to make sure that I end up with a square matrix. I multiply that through, and then I end up with this z transform times y. So once I have this, now I'm ready to go ahead and do my linear algebraic solution. Remember, z transform z is not equal to 1. Right? That was z inverse z would be equal to 1. So what I have to do is take a, and then I can do my back division. Oops, I guess back division times what's on the right-hand side of that equation. Back division of this, I'll put parentheses in here, z transform y. Okay, so now we can do out our matrix math. Let's do an example of this. We're going to go back to fitting our second order equation. So just like we saw before, here I've taken a bunch of x's, here I've taken a bunch of y's, and we're going to do this, but we're going to use the general form of the solution. And we're going to do this in MATLAB. So now I'm back in MATLAB. I've gone ahead and entered the data from the table into MATLAB. So here I have X, here I have Y. Remember, in this case, I need to have a vertical vector for my X's and a vertical vector for my Y's. So I'm going to, if you remember back, I can use this little apostrophe, and that'll turn my X's, which are now horizontal, into a vertical row, and I can do the same thing for my Y's to turn them into a vertical row. The next step is I have to generate my Z matrix. So we need to go in and we need to set our Z, and we want to have first a column of 1, right? That first column is going to be 1 because there's no X dependency. So I can use the ones command in conjunction with size to make sure that I have a vertical column of 1s. Then I can concatenate in this just X, and then I need my X squared term, so I can just type in X squared down there. Enter, and we should have this nice Z matrix. Right? So now we have everything we need. We have the Z's, we have the Y's. Now we're ready to go ahead and calculate my A's. So remember, we said A was equal to Z transpose times Z, back division of Z transpose times Y. Now when I hit enter, I now have my A equation. Right? So this is telling us that our overall equation for this, for those points that we entered in, was Y equals 2.4786 plus 2.3593x plus 1.8607x squared. Okay. We've got our x's. Sorry, we have our a's. We now have an equation for x. Let's go in and calculate out our errors in MATLAB. So the first thing that we're going to need is our sum of residuals. So let's call this SR for sum of residuals. And remember, we're going to take the sum, so we can use that sum command of each y minus the calculated values of y. So we can get that by using z, so that z matrix times our a's, right? That's how we formulated that question originally. Now we need to square that difference for that sum. So we need to do this one element by element. We've got that dot caret in there, ready to go. Hit enter. Make sure that we use lowercase, and we have our SR. Right? That's how much error we have in this value. Now, if we want to go in and look at our different fit profiles, so let's say our standard error, we can do that in MATLAB as well. So let's call this SYX for standard error. Remember, that's the square root of that sum of squares residual over how many data points we had. Well, we can calculate that relatively easily with length of x minus how many, what's the highest magnitude, which is how many a's we have, so length a. I think I have the right number of close parentheses. Needed one more. So this is going to give us that, that error. We can then finally calculate our squared value in MATLAB, where we say r squared, or r2, remember, is 1 minus SR over sum of the variance of y, so we can calculate that directly. So that's each value in y minus the average, or the mean, of those y's squared. And once again, I think I have the right number of parentheses. Yes, I had the right number of parentheses, but no, I need to just, there we go. Okay, so this is telling us that our fit has this unaccounted for variance of, which is very low. So r squared is 0.9985. We have a very good fit in our system. Good. So this is now going to end our talk of general linear squared fits. You've seen us do it taking derivatives, using basis sets, and then in MATLAB. So let's go back to PowerPoint and talk about our last topic of the day. Let's talk about nonlinear regression. Just as we said earlier that we can turn any linear function that's linear in the coefficients, we can use the linear regression for. Some functions cannot be turned into linear equations. Right? So here's this example where I have coefficients up front. We have coefficients up on top. Right? We can't use linear regression here, but we're still going to use sum of squares error. So we're still going to want to minimize this residual, right? So we can take this equation, put it into my residual equation, and then use some sort of minimization algorithm or minimization methodology to solve it. Hopefully you've remembered your minimization techniques from our second unit. This is where this is going to come in handy. So what we're going to do is we're going to first fit a function, and we're going to use, in this case, fmin search, right? So remember, fmin search combined the different good things about the parabolic method, iterative methods, and the golden search algorithm, all wrapped into one. So what we're going to do is we're going to define a function, maybe say f equals a naught v to the a, and then we're going to put that into fmin search. So this is going to come in here. We're going to put in our function. We're going to have our started guesses. We're going to leave this space here, so that's any extra parameters that we want, but we're not going to put in any guesses. And then we're going to pass in all of the values into f that are going to be minimized. All right, let's go into MATLAB and use fmin search in conjunction with our sum of squared error and see how this is going to go. So first we're going to have, so now here we are in MATLAB. The first thing that we're going to need to do is build a function that's going to calculate the sum of squareds. So we have to actually tell MATLAB what that sum of squared is that we're going to minimize. So let's call this FSSR. So our sum of squared function, it's going to take in our series of a's, so those constants, and it's going to bring in our x's and our y's. All right, so we can now calculate the we can now tell MATLAB what our function is that we're going to operate on, right? So this was A1 times x, the x value to our second constant, right? So in this case, we had f equals a v to the a 2. Right here, we're just putting that into MATLAB form. We have our y is equal to the first constant times our x to the a2 power. So this is going to go in and calculate each of those predicted y values in at each of the x values. So now we want to know that residual, right? That sum of squares. So let's take the sum, and now we need to calculate what the residual is. So those are that ym values minus the predicted values, and then we need to, of course, square it, right? So here we have f is going to be the sum of the residual squared. Okay, so then we can go in, call an n to that function. I'm just going to save it really quickly. So now we can call that. Now in my command window, I can enter all the x's and y's. So I've already gone ahead and done that to save time. I've just copied over those values from the PowerPoint. So here are all those x's, here are all the y's. Now I'm going to go in and do fmin search in order to calculate the variables. So remember, we can do fmin search, right? So telling MATLAB to minimize the value of a function. Now we need to tell MATLAB what function. So I use that @ symbol to tell MATLAB what's coming after that @ is a function. So we had called it FSSR up here, so we can put that in there. Now we need our guesses. And let's just say we're just going to guess 1 and 1, right? Pretty innocuous guesses. We're not going to pass any extra information to control how fmin search goes, so just give those empty brackets. Now we need to pass fmin search our x's and our y's, and we're ready to go. So we hit enter, and in this case, the function is relatively simple, and so it comes back quite quickly, telling us that that first constant is 2.5, and that second constant is 1.4. So remember, this in essence is telling us that f is equal to 2.5384 times v, which we represented by x, to the 1.4359. Right? So we can use fmin search in conjunction with this idea of minimizing residuals in MATLAB to solve out nonlinear equations. Once again, this is going to require that we have a initial guess for those coefficients. Remembering back to minimization searches, how quickly we converge, and if we converge at all, is going to depend on how good the guess is and the topology of these minimization of these functions. The last thing that we're going to do is talk about Excel. So far, we've only touched on MATLAB, but we're going to start integrating Excel into what we're working on now that we're getting relatively good at MATLAB. What I've done, if you're unfamiliar, Excel is a program that organizes itself with these rows, these columns across the top and rows across the bottom. Like many Microsoft products, it has different menus across the top, but the most important things to us are going to be this function bar and this insert table and this data table. What you'll notice is I've gone in and I've copied and pasted the data from MATLAB into this table. What you'll see, though, is that I have all these numbers in a single cell and all these numbers in a single cell. This isn't going to be very useful. What I want is to have each number in their own cell. So what I'm going to do is I'm going to click on this B column, highlight both rows, go to data, and then use this text to columns line to split the data into individual elements. When I click that, this window pops up. In this case, we're going to want to tell Excel that the characters or the data is delimited or separated by a space. So here I get to pick my delimiters. I can have a tab delimited file, a semicolon delimited file, comma delimited, space delimited, or anything else. I get to see a preview of my data, which is going to look like this. This is exactly what I want. So I can click finish. I now have the data shown here, where each value is in its own column. If I want, I can change the size of my cells by clicking on these at the space in between each row name, each column name, or each row name. Now that I have this data in, I'm ready to give it a label. So here I have my x's, here's my y's, and now I want to put in my y predicted. So remember, the equation that we're looking for is going to be a times x to some power. So I need to put what those a's are over here. So we had it a1 and a2. So this is where I'm going to put in my initial guesses. Right? So I have my 1 for my initial guess for the pre-exponential, and then the power is sitting over here. I'm now going to go in and use this formula bar to put in the formula that I'm looking for. In this case, I want a1 times x to the a2 power. When I hit enter, it will then auto-populate what that is. Well, this is exactly what we expect. 1 times 10 to the first power is 10. To make my life easier, instead of having to retype this in each of these different boxes, I can go in and I can add in this $sign. And this $sign tells Excel to keep, don't change these rows. These are going to be constant. When I hit enter now, nothing changes. But the benefit of having those $signs in there is I can move my cursor over onto that corner. And it changes from this sort of white-shaped cross to a black-shaped cross. I can then drag it over, and it will automatically populate. But I typed my $signs in wrong, so it gave us zeros. I'm going to go back and correct those $signs. Now when I drag it across, it automatically populates, right? So if I click on this, MATLAB shows me which cells I'm calling from. This is the cell that I want to call from. These are the 2 cells that I want to call from. That's great. If I looked at the case where I messed up, it's calling from the cell that I was interested in, and then it had actually moved the cells that it was calling from over. So that's not what we want in this case. So I'm just going to drag this all the way over here. We can now see the 80, and we can see the two variables that we called. So I now have my predicted x. I can calculate my residual. So we'll put that in here. And I can do my actual minus the residual squared to get that error. I can once again drag that equation across. In each of these boxes, it's going to take y minus yp and square it all the way across. I'm then going to set up my sum of the residuals over here. So here in my formula bar, I'm going to use the sum command. And here I'm going to drag my cursor across the screen. We can see that we have B7 colon I7. This means it's going to sum from B7 all the way to I7. I can close that parentheses, hit enter, and it will sum that to give me my residual. I'm now going to go ahead and minimize this residual using Excel's minimizer command. Before I do that, though, I have to install it. You should look and see in your data tools, if you click on this data bar, see if you have the word solver showing up anywhere. I don't have it, so I need to go in and put that into this sheet. So if you click File, then you go down to Options, Add-ins. Let me make sure that I'm correctly showing my screen. If you click in File, then Options, you should see this screen pop up. When you scroll down to Add-ins, you should see Manage Excel Add-ins. Here's where you want to click Go. All you want to do is click on this Solver add-in and click Go. It's going to take a second, but when it comes back, you should see this Solver button pop up over here. So Solver is what we're interested in. So Solver is going to solve a problem for us in Excel. So first we get to pick an objective cell. So what is it trying to solve? Well, it's going to try to target what's happening in K7. This is where I have my sum of my residuals. We are then going to say we want Excel to minimize that value, so make that value as small as it possibly can. And it's then going to do that by changing this A1 and A2 value. So I can put those parameters in there by clicking on them, dragging down, and then hitting enter. I could add constraints, right? I could add something that says, make sure that A1 is always bigger than 0. When I click, oops, when I click that, that will then show up in that constraint. In this case, I don't want to constrain it to that, so I can remove that with that delete button. Once I'm ready, I can click the Solve button. Excel, relatively quickly, will pop up and ask us if we want to keep what Solver has or go back to what was there before Solver started. In this case, I want to keep what Solver had, so I click OK. And we'll see that A1 and A2 have changed. Not only have they changed, but they exactly match the values that we got out of MATLAB. And we also see that the sum of my residuals has decreased. The last thing that I want to do is map this out. So if I highlight these cells, I should be able to go into Insert, click on this chart, and get these data points, right? So Excel is going to create these data points, this graph for us in here. In Excel, I have several different choices for my graph. I could have picked just this pure scatter plot. I could pick scatter with smoothed lines. I could pick just the smooth lines, and I can pick maybe straight lines between the markers. In this case, I want just points because these are hard data points. If you remember, Excel data points are represented by, data is represented by points. I can then add additional data by right-clicking on the plot and clicking Select Data. I then use this Add button to insert new X's. So in this case, I still want those old X's, so I'm going to select that X. And then I'm going to select this new value of the Y's for the proposed, or the fit version. I can hit Enter, and that shows up now as yellow dots. Right? If I click OK, I can now go back to my set. I probably want to format this a little bit differently. So I can click on the Format button and add a line to that set. Right? So that then gives me the line that would indicate fit points. Often we want to add in extra things to our chart, maybe like an x-axis. So if I go to Chart Design, I can click on Add Chart Element, including a horizontal axis and a vertical axis. Maybe this we call the velocity, sticking with the theme from the example. And here we calculate some sort of force. Okay. And then we could add in a chart title, velocity to force relation. Good. So hopefully this example has shown you not only how to calculate, use minimization in a second way, but it's served as an introduction to using Excel. Remembering we can put data in each of these cells and then write in formulas. And we can use these dollar signs to fix the formulas so when I drag formulas across, they don't change. Then we used Solver and we plotted them as a graph. We'll come back and get practice with Excel again throughout this course. So let's review. Today, we covered polynomial regression, multiple linear regression, and did generalized linear least squared fits. All of these relied on taking the derivatives of our individual linear components of an equation and solving for them, either directly by constructing that matrix, or using the Z transpose Z method in that general linear least square fit that could account for things like sines and cosines of X. We then implemented this, and discussed nonlinear regression where A's were where the constants are not linear themselves, and how we can solve this using minimization techniques to minimize the sum of squared errors, which we then conducted in both MATLAB and then Excel. And so we got our first taste of Excel. I hope that you found this lecture interesting, and I'll see you in class.